Hello and welcome to another video. This one's very much aimed at anybody who watched the Weierstrass substitution video with it failing. I want to talk a bit more about when integration by substitution fails, when we don't use a function which is one-to-one. And I want to thank Prince Sirin for his comment here because I've got to be honest, I was a little bit baffled as well when I started thinking about it. It had never really occurred to me that when you use a particular type of substitution, namely when you choose x in terms of u, not when you choose u in terms of x, but when you choose x in terms of u, you must make sure that it's a one-to-one function. Yeah. So, for example, when we make the trig substitutions, they're the classic example. And that's why you were absolutely right, Prince Simon, when you suggested sticking to inverse sine, inverse cos, and inverse tan. But I wanted to talk a little bit more about that today and a little bit about why, if you were to use functions which don't correspond to, traditional inverses, shall we say, why it can succeed still. It's absolutely fine. The key thing is that you shouldn't choose a many to one. Well, and we can't describe it as a function, can we? You shouldn't use something which is many to one. You had a lovely example of this as well. I particularly like the example which you linked to of sine x over 1 plus sine x dx, yeah, between 0 and pi. If you say let t equal sine x, you're going to end up proving that that integration, which doesn't equal 0, equals 0, because we get dt by dx is cos x, and so we get dt is root 1 minus t squared dx. And so we plug it in, and we get t over 1 plus t multiplied by 1 over root 1 minus t squared dt. But the key thing is when you plug the limits in, x is 0 and x is pi and x is 0, you get 0 and 0 here. Okay, I think I can explain what the problem is here now, and I think it's got everything to do with the parametric form which you think about this being written in. Yeah, that's what I think it's really about. The only thing I disagreed with in your comment actually was this little point here. You said from 2 pi over 3 to 4 pi over 3, tan x over 2 is not 1 to 1. I'm not so sure that's true, so I'm going to try and convince you otherwise. If here is the graph of y equals tan x over 2, yeah, so I've just sketched it. You'll notice it's just like y equals tan x, but it's been stretched by a factor of 2. And on this graph, I believe that if you go from 2 pi over 3, which is roughly 2, so it's about here, and go up to 4 pi over 3, which is roughly 4, so say down here, a little bit more, I think if we just looked at that section of the graph, I believe it is a one-to-one function, yeah? Because the key thing is about one-to-one is if you draw a horizontal line, you only hit the graph once. Well, in this range, anywhere we draw it, we're only hitting the graph once. So I do think it's one-to-one, which I think is why my method succeeded in the end. But I agree with you, though, that you have to be super careful. My method succeeded essentially because tan of x equals tan of x plus pi. And that applies for x over 2 as well. Generally speaking, tan of stuff, if you like, is equal to tan of the same stuff plus pi, yeah, and that's why my method succeeded. But yeah, it is subtle. Anyway, let's talk a bit more about why these things fail, because like you said, I want to bury this problem. I completely agree. It's like one of these pernickety kind of things in maths where it's all about like fiddly little bits, and you're like, oh, but it is important. So and I've learned plenty looking at it, so I'm really appreciate it. Okay, I'm going to first consider integrating between 1 and 4 root x dx. I'm going to use a really silly substitution here. I'm going to let x equal u squared, just because I want to talk about what would happen if we took different values when we use this substitution for our u values. Yeah. Now, typically you'd say, okay, dx by du is 2u, so dx is 2u du. Yeah, silly way of integrating it. I completely agree, but let's do it anyway. Okay, so our limits are in terms of x. Let's put them in terms of u. Now, typically, you would just take the positive root of this, wouldn't you? Well, you put in 4 here, and you take u is 2 and u is 1. And therefore, we've got root x, which is u, multiplied by 2u du. And so we've got 2u squared. I'm sure you're thinking, get on with it, because this is easy. This gives you 2u cubed over 3 between 2 and 1. and you get the right answer, which is 16 over 3 minus 2 over 3, which is 14 over 3. Okay, what would happen? What I'm interested in is what would happen if we took minus 2 and minus 1 here. In other words, if we said, you know what, I'm only going to, when I square root here, I'm only going to take the negative values, because that would still be a one-to-one function, wouldn't it? If we just said, I'm not going to take any of the positives, I'm only going to take the negatives. It's the equivalent of saying, you know, the function y equals x squared, where if I'm going to restrict the domain so that the inverse exists, most normal people say x is greater than 0. Well, I'm going to be abnormal and say x is less than 0. So I'm only going to take that. That's still a one-to-one function. Let's see if the integral works. Okay, let's turn this off for a second just so I can move around the screen. Okay, right, so let's try that. Well, if I did it the other way around, what would I have? I would have the following. I would have had exactly the same, but it would have gone minus 2 minus 1 here, and I would have had 2u squared du, and I would have ended up with essentially the negative of the answer, yeah? 2u cubed over 3 between minus 2 and minus 1. And so I would have ended up with minus 16 over 3 plus 2 over 3, which is minus 14 over 3. Now, why did it go wrong? Well, let's talk about the parametric form. The Cartesian form of what we were dealing with was essentially y equals root x, yeah? And remember, when you're integrating, you're looking at the rectangles of height y and width delta x, essentially. That's what we're really doing. Well, if you instead look at the parametric form and say, well, x can be equal to u squared and y can be equal to u, that's like a parametric form with u as the parameter, yeah? And when you take the negative values for u, clearly the y coordinates are negative, but the x coordinates are positive. So it's the equivalent of not taking the square root of x there, but instead taking y equals minus root x down here. You see, the parametric form will show you the whole curve, won't it? Yeah, so it will take you all these ones down here. And that's why we're ending up with a negative answer, because all our y coordinates are negative. So that solves nicely why we don't have to take, we don't have to be really conventional with our function, yeah? We can still take other values other than, and I'm thinking specifically here in terms of arc sine, arc cos, and arctan. Now, don't get me wrong, I know arctan is between minus pi over 2 and pi over 2. Same with arc sine, and arc cos traditionally is defined to be between 0 and pi. But I'm going to say, what if, basically? What if on another universe we decided to define arc sine in different ways? And I want to show you that still, the method works and holds in certain cases if you're careful. Anyway, let's choose another one. Let's learn a little bit more about what we're doing here. Let me let's clear all the ink. And let's think now about, right, what about if we were doing, this one. Okay, 1 over root 1 minus x squared, yeah? Now, this was a good example that you left, and it was an excellent example between 0 and a half. And I thought immediately, yeah, let's be different. Like, I think we all know that if you let x equal sine theta here, yeah, everything's going to work out hunky-dory because you get dx is cos theta d theta. And so this ends up being integrate 1 with respect to theta, yeah? Because you get 1 over root 1 minus sine squared, which is 1 over cos multiplied by cos theta d theta. You end up integrating 1, don't you? Now, normally we'd have 0 and pi over 6 here, and we'd get the right answer. But what would happen if instead I took the next values on the sine curve? So sine, if you've got sine theta equals a half, you could also have 5 pi over 6 here. And let's take the next one for 0, which is going to be, okay, that will be pi, yeah? If you do that, then you end up with a negative of the answer you should get, because you'll end up with theta, from 5 pi over 6 to pi. And so you end up with minus pi over 6. Now, why have we got the negative answer? Well, the answer lies in parametric equations again. It really does. If you think about, because what we've really done was we've parametrized this. I think I've said that wrong. We can say y is going to be equal to 1 over cos theta, and x is going to be equal to sine theta, yeah? That's like a parametric version of y equals 1 over root 1 minus x squared, yeah? And I hope you can see where I'm getting these from. It's because y is just this value here. And what I want to show you is if you're operating between these limits, i.e. if you're letting theta vary from pi over 2 up to pi, I want to show you that on this curve, this graph would be, the y coordinates would be negative, yeah? Because obviously cos theta is going to be negative from pi over 2 up to pi, and so y is going to be negative. And so I think the graph looks something like this. Please draw it on something like GeoGebra is one I use, but Desmos or something like that. Be careful, make sure your graph drawing software package allows for plus or minus before the square root, because now I completely agree as well, by the way, that root of 64, look at that, root of 64 is just positive 8, it's the positive root. But if we parameterize it, which is what we've really done here, we've turned it into a parametric equation when we're using the substitution, then all of a sudden y can take a negative value from those values, and that's why we're ending up adding up a series of negative negative y coordinate heights, and that's why we get a negative answer. The area lies below the x-axis, and that's why we're getting a minus pi over 6 here. But I fully invite you to draw it. I tell you what, it's easier. Maybe I'll quickly draw it on GeoGebra for you right now. Can I open this up? I think it should work because I think I'm just sharing the screen. GeoGebra. Okay, right. Let me just show you that if I was to type in the following, A equals, I need to add a slider. Let's add theta, or let's just call it t, and we'll do it from 0 to 2 pi. Just wanted you to see this, okay, and then we'll put a in as, I think it was sine t, and then 1 over cos t. Okay, and then we'll just set a trace on a. You don't necessarily see this if you type in the square root, so it does get confusing. Okay, right. As you can see, initially I'm at the top of the cut graph, yeah? But as soon as I get past pi over 2 is about 1.5, suddenly I'm at the bottom and the y coordinates are all negative, yeah? That's why I'm getting a negative answer from that. That's why it's letting me down. But it'd be perfectly okay to do it as long as you're recognizing when the graph is negative, yeah? Okay, so all very entertaining and interesting. Now, what about some of the ones we were looking at? Now, the next one I wanted to show you was just the one which you mentioned, the sine t over 1 plus sine t. So let's clear the ink and look at this. Okay, if we're integrating from pi to 0 of sine t over 1 plus sine t, why does this one fail, dt? Now, this is a bit different, actually, and we have to think about this because I don't think this is just about the fact that this function is, or could be considered once you put it in parametric form as many to one. It's about arcsine, this, and you'll like this because it's about the range of arcsine when you draw it on a graph. Now, okay, so essentially what we've got is y equals sine t over 1 plus sine t here, yeah? But then, I think it was x we were using. Can I change that to x? Okay, let's change it to x. That's better. Okay, now if we were, that's the Cartesian form. If we were to make a parametric equation of it, well, it would be pretty easy to do because I think we were choosing that x equals sine t in our substitution, yeah? And it all went wrong, didn't it? And you end up with 0 and 0. That's because of what can happen with parametric equations. It really is. Now, if we think about the parametric form, you've got x is arcsine t, t is arcsine x. No, arcsine x is t. Yeah. Yeah. What was this? I've messed this up. I do apologise. I've absolutely messed this up. It's the correct substitution you suggested was t equals sine x, wasn't it? Now that's making sense. T equals sine x, and all hell broke loose, didn't it? Now that means that x is arcsine t, whereas y is going to be t over 1 plus t, yeah? Now, if you draw the parametric equation of that, then this is what you end up with, and it's interesting to see this. Let's just go to a new one, and let me make this nice and big. Okay, so if we draw the original function, which is y equals sine x over 1 plus sine x, we get this graph, lovely, yeah? Whereas if we only draw the parametric version, the problem is the parametric version is restricted, and it's because of arcsine. Arcsine causes the problem here, because if I now type in a equals, oh, I need a slider, let's call this t. I think there is another way of doing this, actually, a more sensible way. Now, as I'm doing arcsine on t, I'm going to have to make this from -1 up to 1, yeah? And because of the way arcsine is defined by convention, that's all it is, a convention, to be between -pi/2 and pi/2, this is only going to sketch some of the curve when I do this, unfortunately. So when I type in a equals, right, what is it, arcsine t, and then t over plus t. Okay, hopefully when I move this slider, I trace out some of this. Oh yeah, let's set a trace so you can see it happening. Okay, right. We can see it's only sketching some on a curve, and that's just because of how we define arcsine to always strictly be between -pi/2 and pi/2. It will only go up to pi/2, just like you said, yeah, it's only going to be valid for pi/2 there, so that is a problem. Now, there's easy ways of fixing it. You could use the fact, for example, that sine x is sine of pi minus x, which is why you get symmetry here. And I'm sure I've seen an old step or mat question where they get you to prove that that integral, this very integral, is, you know, if you go from 0 to pi/2, by using a clever substitution, let u equal, well, let pi minus, let me actually write it down. I'm certain that we could do a clever substitution to prove that the first half is equal to the last half here, yeah? I'm going to invite you to prove that 0 to pi/2 sine x over 1 plus sine x dx is equal to, from pi/2 up to pi, sine x over 1 plus sine x dx. You can do it with substitutions without actually evaluating either integral, which is interesting, isn't it? Like, it's really quite quick to do, I think, as well. So that's one way of handling that kind of integral. But the other thing as well to say is, when we're dealing with, I mean, that's a problem with, you know, and this is where this ties in very much to your approach, yeah? We could, of course, sketch out the rest of this by doing things like this. If I just add 2 pi to what I had before, so let's make b equal to, what is it, arcsine of t. Oh, but let's just add a couple of pi's, because sine repeats every 2 pi. And then we'll have t divided by 1 plus t again. Okay, right. And this should be able to, this will basically sketch us this bit, I think, yeah? And then, you know, we could just generalize this result and it'd be easy. But as you can see, you're still finding the same areas, or you're still looking at the same y coordinates. That's what's key in these integrals. You're still looking at the same y coordinates. Let's say a trace on B and hope this works. Okay, right. There we go. We're sketching out both sides of it. And I could do that for 4 pi and for 6 pi, for here and here. And to get the other half of that, well, this is where sine and cos are both awkward, aren't they? Because sine has like, you do, you know, 180 minus if you're in degrees, or pi minus. If we do that here, then we could easily sketch out the rest of it. In fact, let's do it. C equals, right, so let's have pi minus arcsine t, and then t divided by 1 plus t. Okay, and then let's set a trace on C. And let's move our parameter. Okay, now we're sketching out the whole of the curve, yeah? So we can use, like, we can build functions out of arcsine to create the whole parametric curve, but it's really about the parametric form. That's what I want to, that's what I've realized anyway, and I hope it makes a little bit more sense out of it to you as well, and anybody else watching. It's really, what you're doing there with an integration by substitution is you're doing parametric equations, and that really helps you decide whether the y coordinates are all of a sudden negative or something like that. and why a lot of these integrals break down. But that one from 0 to pi breaks down because this bit is actually the mirror image of that. And so you're actually dealing with sine of pi minus x, and it basically cancels it out. And it's because sine is an odd function, really, that minus sine of minus x is sine of x. That's what's happening there. So that's a real problem. Now, what I did think about, why I was slightly confused about what you said with your substitution. I think your substitution will work perfectly, by the way, absolutely perfectly. And I fully invite you to have a go at it. If you break it into two parts, you're definitely going to have to break it into two parts. Because asymptote is a problem, definitely, because you've got an infinite limit there. You've got an infinite y coordinate. That's what the problem is. But if you do it from 2 pi over 3 up to pi, but there your substitution should be just t equals tan x over 2. No plus pi required. But your next one from pi up to 4 pi over 3, that's when you're going to need to add a pi, like you did with your, I thought that was very clever. You're absolutely right. This substitution you suggested, and you're right to think of it in terms of arctan as well. So where is it? Where was your suggested one? You said, I got blah, blah, blah. I can't find it now. Because you said you got the right answer, didn't you? But just not in the actual form. And I couldn't quite work out why you hadn't got it in the actual form. Because I think I get it in their form. I thought it worked out perfectly for me. Where is it? Where are you saying this? Yeah. Oh, maybe it was in the original one. No, yeah. Up here maybe. Yeah, this substitution. Yeah, I think that's very clever, and I think that works fine for pi up to 4 pi over 3, but it doesn't work for 2 pi over 3 up to pi, just because you're using the wrong range for the wrong bit. From 2 pi over 3 up to pi, basically here's the bottom line. Weierstrass substitutions are fine from minus pi to pi, but also from pi to pi up to 2, pi up to 3 pi, and from 3 pi up to 5 pi. You've just got to be careful with the discontinuities at minus pi, pi, 3 pi, 5 pi. Note that they're not the same as the discontinuities on tan, because you've got tan x over 2, so you've stretched it by a factor of 2. I hope that makes a bit more sense. I'm very happy to quickly, I think you'll be fine now if you use the original substitution, the normal substitution from 2 pi over 3 up to pi. I think that's where you made a mistake, perhaps, that you should have, and that's why the form looked different, that you should have had this just used in a normal substitution, and then from pi up to 4 pi over 3, use your very clever x equals 2 arc tan t plus pi. By the way, though, it's completely unnecessary, because tan, let me just write that down again. So this is the same as x over 2 minus tan t equals x over 2 minus pi. Yeah. If I can just write this down, it is equivalent and there's no need to do it, but I still thought it was very clever what you were doing. It's basically what you were doing is t equals tan of x over 2 minus pi, wasn't it, essentially? Now, I think that's the same as just because of the symmetries with tan. Generally speaking, tan of x equals tan of pi minus x, and so it doesn't end up mattering. It really does. You can always add a pi to it, can't we? So we can add here, tan of x over 2 plus pi tan of x over 2 minus pi is the same as tan of x over 2 minus pi plus pi, and so it doesn't matter. It really doesn't, because they give you exactly the same y coordinates, which is what we care about. Okay, I hope that made a bit more sense. If it didn't, I'm sorry. It's helped me anyway, so I'd like to thank you for pushing me on that one, because it's made me really think about how integration works for those kinds of substitutions. So all the best, and keep up the good work. Best of luck in the exams. Bye bye.